All right, hello everyone. Today I will be helping present the course project. Our project was entitled Using Iowa Liquor Sales to Predict Future Alcohol Sales. Today I'm joined with Kyle Leonard, Joseph Russell, and Barris Tezel. Before we actually go into the results of our course project, it's important to get a little bit of background of why we were interested in this and how we actually came to a conclusion. So during the onset of the COVID-19 pandemic, alcohol sales reached all-time highs. And since then, alcohol sales have continued to reach all-time highs. Because of this, our group has been really interested in determining what exactly contributes to higher amounts of alcohol sales. So for example, we are really interested in seeing how unemployment, education background, income, and different liquor categories affect alcohol sales. It's also important to note how we will arrive at this conclusion. So we are using data provided by the state of Iowa and the American Community Survey. In this data, we will have information concerning sale dollar amounts in each county and city of Iowa. And also it's important to note why this may be important or useful in the world. So by using machine learning methods, companies will be better able to accurately predict alcohol sales in a particular area. Doing so will allow them to determine where exactly their resources are most needed and where exactly their resources can be the most effective.
All right, so like Josh previously said, our source of data comes from a 5-year amalgamation of data from the state of Iowa itself, as well as results and findings from the American Community Survey. As a result, this data set can be considered as a merged data set due to a combination of sources that come together into one set of statistics. Our variables range from qualitative to quantitative, and a few examples of our qualitative data are one category of liquor. This data set is subsetted into 10 separate categories of liquor, like vodka, gin, whiskey, etc. And then also we have county and city of residence variables, which are location metrics that obviously can't be assigned a numerical value. Some of the examples of our quantitative variables are income, which is measured by median earnings in a certain city or region of Iowa, population by race, which is split into 7 different subsets of different race categories, and sales dollars, which we initially identified as our dependent variable, but realized that we had to make a slight modification to adjust and account for population. So in this process, before creating our inference model, we needed to make some of these changes to create a more accurate sense of the data we were looking at. So like I was saying before, we created a per capita sales variable, which was created by dividing the sales dollars variable that was previously provided by population. We realized that sales and population went hand in hand pretty closely together, so we couldn't sacrifice the dependent variable without accounting for population itself. Also, we had to modify some of our explanatory variables that were present in the data set already. We changed income to income by thousands, or income dot thousands, by dividing by 1,000. This allowed for a much easier interpretation of our coefficient estimate. And we also altered some of our education and socioeconomic status variables like high school, bachelor, and unemployment to create percentages and dividing them by 100. This was all for ease of interpretation and much easier coefficient outputs that led us to a more accurate and palatable regression.
So we included 13 different explanatory variables, the first 3 of which are percentages of the population with high school degrees, bachelor's degrees, and the unemployment rate. As Kyle mentioned, we divided these variables by 100, so they range from 0 to 1, making our coefficients larger and making it easier to assess the relative impacts. We also included median income in thousands of dollars and 10 different liquor categories as dummy variables, including vodka, tequila, amaretto, gin, brandy, schnapps, rum, whiskey, and spirits. We also account for miscellaneous liquor types, which is the base case and thus not included as an additional dummy variable. So we use these variables to predict and assess their impact on per capita sales in dollars, which is total sale dollars divided by the population. So we used a multiple linear regression model for inference, including the 4 continuous variables and 9 dummy variables and our dependent variable of per capita sales. So what we found from our inference model is that the results were fairly consistent with our expectations. Unemployment was a very important variable in this case, and our model suggested that a 1% increase in unemployment was associated with an estimated increase in per capita sales of about $1. Our education variables also had highly significant coefficients. Although these variables are highly correlated, estimations across other models, not including the other variable, demonstrated similar results where the percentage of high school graduates negatively impacted liquor sales, while the percentage of bachelor's degree holders had a positive impact. We found a negative relationship between income and per capita sales with an estimated decrease of 29 cents per $1,000 increase in median income. And finally, most of our liquor category variables had pretty significant coefficients, notably whiskey, vodka, and rum, which were associated with respective increases of $20, $9, and $4.50 in per capita sales.
So now moving on to our prediction model, we just want to preface by saying that our group removed some of the variables that we believe would be harmful to the prediction model that came from the base data set. So variables like income, high school, bachelor, and unemployment were removed and actually altered. And we talked about including them as a percentage form already. Additionally, sale at dollars and all population variables were removed from the prediction model as a dependent variable already comprised of these variables. So after removing these variables, we decided to move on to an 80-20 split, where we then created a train/test sample. And then now we wanted to create 5 forms of different regressions. So we wanted to do this to kind of predict or see which regressional analysis was most accurate. So we did an OLS regression, a backward stepwise regression, a forward stepwise regression, a ridge regression, and then a lasso regression. So after running the OLS, backward, and forward regressions, we decided to extract the best formula by looking at the highest adjusted R-squared value. And then for the ridge and lasso regression, since they're a little bit different from the previous 3, we used a cross-validation to then extract the best model. And then after extracting the best formulas for each of these regressions, we then created an accuracy data frame to test again, to kind of compare the mean squared errors between the different models, so we can understand which regressional analysis was the kind of the best fit for our case. So we then calculated the MSE for each type of model and then assigned its value into the accuracy data frame and then compared it. So moving on to the next slide, we can kind of see the key findings of our study. So after running the regressions through the accuracy data frame, we discovered that the ridge regression actually was the best prediction model, as it had the lowest MSE. As you can see at the chart at the bottom, it had an MSE of 73.87, which is considerably lower than the other 4 models that we ran. So we also determined that the OLS regression model ended up being the worst prediction model, as it had the highest MSE of around 79.74. However, we then also decided to look at the relative MSE, which we used we used the OLS regression model as a base. And then from there, we also saw that the ridge regression was once again the best performing regressional analysis. And then thank you so much for coming to our presentation.